observations of NWP comparisons during YOPP. And Zen is one of our MODF makers, and his sites are Whitehorse and a Callaway.
Perfect. Good morning, everyone. Thanks very much. So in this talk, I'm going to discuss sort of an overview of some of the enhanced observations that were conducted in the Canadian Arctic by Environment and Climate Change Canada. And towards the end of the talk, I'll discuss some of the comparisons that we've been doing with NWP models, just as to highlight some of the studies that we've been looking at. So, well, close to a third of Canada is north of the Arctic Circle. And at the same time, there's relatively sparse observational coverage. So in the context of YOPP, there was this question of, what can we do to sort of fill some of these gaps? And at the same time, there's increasing human and economic activity, as well as increasing search and rescue events. So for instance, air traffic has increased from 400 transpolar flights to over 12,000, almost 13,000. There's also, of course, the opening of the Northwest Passage. And in terms of search and rescue events, there are 240.5 incidents per 100,000 people. And to give some context of these numbers, that's 2 orders of magnitude larger than 2 of the southern provinces, BC and Ontario. So this is quite a large deal in the Canadian North. Now, weather-related hazards, so specifically blizzards and low visibility conditions, are primary factors that affect search and rescue, navigation, and mobility. And moreover, these hazardous conditions are expected to become more frequent, longer in duration, and less predictable under climate change scenarios. Now, ECCC provides the meteorological services to Met Areas 17 and 18, which you see in that figure in the top right. So there's this need to improve the Arctic weather forecast and provide relevant weather information for the local communities. So that takes us to YOPP and some of the enhanced observations that were conducted by ECCC during YOPP. So we had increased coverage of the Arctic observations, particularly during the special observing periods, or the SOPs. So for instance, there were additional radiosonde launches, buoys, in situ snow and ice monitoring, as well as 2 aircraft campaigns that took place during the SOPs. There was the commissioning of the Canadian Arctic Weather Science supersites at Callaway and Whitehorse, which I'll talk about more in a minute. But essentially, there's model high-frequency time series output in a 7x7 grid at and around each of these supersites. There was the regional forecasting offices and the Canadian Ice Service that provided their evaluations of available prediction systems, and we've collected this valuable user feedback. There's ice stress measurements off the Labrador coast and validating ice thickness retrievals from ICESat-2, and measurements of snow distribution and microstructure for validation and modeling. And finally, there were also some post-processed products, specifically blizzard, precip type, and fog forecasts that were discussed yesterday by Bill Burrows. So if we look at these 2 figures, the figure on the left shows the locations of some of the supersites, so by the red stars. So the one on the left red star is Whitehorse, the right red star is a Callaway, and at the top is Eureka, which also published MODFs. And the blue stars indicate the locations where we had additional radiosonde launches during the SOP. So we went from 2-time daily to 4-time daily launches. And with respect to these additional radiosonde launches, there's a really interesting study that's just been published by La Roche and Pone, shown on the right, where they looked at the forecast sensitivity to observation impact for the radiosonde stations. So what's shown here, each of the circles are the different radiosonde stations, but the ones that have a green box around them, these are the radiosonde stations that conducted additional launches during the SOPs. And so this paper goes in detail quantifying the positive impact that these additional launches have had. The actual color of the circle relates to the FSOI score. And just one example, if we look at Cambridge Bay, which is just left of center of that map, the circle is a very, very dark brown color. So there's a very strong positive impact as a result of having additional radiosonde launches at this particular site, as just one such example. So in addition, in terms of Arctic buoys and the observations over the ocean, there was a need to address the significant gap that exists in the polar ocean observing system, which is hindering the reliability of the ocean and sea ice forecasts. So this figure on the left shows, for example, in 2017, that there's a historical lack of buoy coverage in the Eurasian basin. So that's this red circle you can see sort of to the right of the center of the figure. And if we look at the same figure in 2018, we see how we've increased the observations to sort of fill in this gap and address this, the gap that was occurring there. And so as such, here's an example of the Arctic Heat Alamo floats and the ECCC Argo floats that were taking observations during the YOPP periods. So right after this talk, actually, Greg is going to do a talk on this result, as well as some OSCs and some studies that have been done using these new observations. There's also the deployment of sea ice sensors near the community of Nain, which is off the Labrador coast. And the goals here were to provide sea ice information to the local communities, to study the internal ice stresses in the land-fast ice cover, and to improve the sea ice forecasts. And what's some of the ongoing contributions are, well, firstly, these instruments have been deployed since 2017 on a yearly basis, and they're being used by the community. There are in-situ observations of thermodynamic and dynamic processes, and these records are being used to assess the thermodynamic parameterizations in the ECCC systems. And this is essentially helping us guide the model developments for future versions of the ECCC systems. So what's shown here, for instance, is the observed ice mass balance from these measurements, and then some of the test cases where they've looked at simulated thermodynamics. So for more information for this, there's actually a poster just outside that goes into a lot more detail for these results, if you're interested. And then finally, we have the Canadian Arctic Weather Science, or the CAWS sites. So 2 super sites were established in the Canadian North to address these 4 objectives that you see listed here. But in the context of YOPP, I'll just sort of focus on the first one, which is, of course, to advance the knowledge of Arctic weather phenomena and their representation in NWP systems. So the 2 sites that were commissioned are Whitehorse and a Callaway. So Whitehorse is the star on the left, Callaway being the yellow star on the right. And they were selected because Callaway and Whitehorse are weather and transportation hotspots. So the figure on the left shows the northern marine transportation corridors, so both the primary and secondary routes. And we see Callaway is smack dab in the middle of a lot of marine traffic. But also, Callaway and Whitehorse are very important for air traffic. They're sometimes referred to as the gateways to the north, Whitehorse being for the western Arctic or the central Arctic, and Callaway, a lot of air traffic going to reach the rest of the eastern Arctic and central Arctic. Now, on top of that, these 2 sites are situated sort of at the start of or at the end of storm tracks that commonly occur in this part of the Arctic, as identified by our operational forecasters. So that means they're right in the middle of some of the severe weather that occurs in the region as well. So we've deployed a number of new remote sensing instruments and technologies to these 2 super sites. The concept was that these instruments have a high maturity level, so it makes them relatively easy to deploy to the field, but they're fully automated and remote controlled. So there is no observer at the site. The site is totally automated. No one actually is physically there. The instruments operate 24 hours a day, year-round, conducting continuous observations. And they have the capacity to probe boundary layer meteorology. So they have high vertical and temporal resolution. And our focus has been on winds, light precip, water vapor, cloud microphysics, and radiation fluxes. And all this was done to support the assessment and improvement of NWP models, so verification, evaluation, process studies. And as an added bonus, the observations that we conduct at these sites are compatible with or similar to some of the space-based technologies. So for instance, we have ADM Aeolus, which is a Doppler wind LiDAR in space, and we have 3 Doppler LiDARs deployed at the ground at these sites. There's the GPM satellite, and we are conducting calibration validation studies at these sites looking at precip and clouds using the same ground-based observations. And then there's the upcoming EarthCare mission looking at radiation, and the NASA CSA AOS mission looking at radiation clouds and aerosols, where we have, in some cases, the identical instruments already located at the ground that'll enable some of the CalVal exercises in the future. So this is a Callaway, and our site's located right next to the airport runway, which is in turn located right next to the town. And this is what a Callaway, or the site, looks like in late summer, early fall. And I've just highlighted some of the instruments that we've installed at the site that you can see here. Everything from water vapor LiDARs, Doppler LiDARs, lots of in situ observations at the surface, precipitation imaging packages, for instance, K-band, weather radar, and radiation flux sensors as well. At Whitehorse, we have a very similar suite of instruments that were set up and running throughout YOPP. The difference with Whitehorse is it's in a valley situated between two mountains, so very complex terrain in Whitehorse compared to Callaway, which is a coastal site in the Arctic tundra. And all our observations were delivered in near real time to obrs.ca. So this is a publicly accessible website where we put up the raw data, processed products, the plots, and so forth. So the idea was that operational forecasters can look at some of these, the data coming out of these sites in near real time to aid with, for instance, nowcasting. Now the raw data is available on the Government of Canada Open Data Portal, but we've also published these MODF files that have been mentioned earlier in the talks on the YOPP Site Data Portal, and this is what's going to help enable international NWP model intercomparisons. Now, in terms of some of the comparisons that we've done, some of the studies that we've done looking at comparing the ground-based observations to the NWP model output, one of the things we've been looking at, for instance, is I'll talk a little bit about a study we looked at looking at the winds, not just at the surface, but the vertical structure of winds, so the upper air winds. And we did this both at Callaway, which you see here, Whitehorse, and then we have a third site, a mid-latitude site in Squamish, BC. So this is very close to Vancouver. And this enables us to look at not just how well are the NWP models performing in the Arctic, but also how well do they perform at mid-latitudes, just as a comparison. And so for this study, we just looked at the ECCC NWP models, which you can see the different domains here. So we looked at the RDPS, 10-kilometer resolution, HRDPS, and the CAPS model as well. And you can immediately see the difference in topography. So Callaway, flat tundra, coastal. Whitehorse is you're sandwiched between mountains, and Squamish is a bit of a mess where it's extremely complex, mountains everywhere, and you're close to the coast. So very challenging to do some of the comparisons at Squamish, for instance. And so these are the results that we've produced for just looking at the upper air winds. We have similar results for looking at water vapor, but I'm not going to show them here today. What's different looking at this vertical structure is we are comparing the model output to the Doppler LiDAR. So usually these are done for radiosondes, twice a day, but the Doppler LiDAR takes a wind profile throughout the boundary layer every 10 minutes. So we have a lot of data, every 10 minutes, every 3 meters in vertical resolution. So what's shown here in these figures is the results for Callaway, Whitehorse, and Squamish. This is the 2016 to 2019 average bias, which is the dashed line, and the RMSE, which is the solid line. And what we found is that there's better agreement at a Callaway, mainly because it's tundra, compared to Whitehorse and Squamish, which is the complex mountainous terrain. We've also investigated seasonal performance, and we found that there was no increase in the bias or the RMSE with a forecast run hour. And we found similar results for water vapor using a dial instrument, except that we found much better performance in the wintertime. And we believe that the reason for that primarily is there's just so little water vapor in the Arctic during the winter that you don't have a lot of variability, you don't have a lot of change occurring. Now, one of the things I want to point out in this figure on the right here is the black arrows indicate the approximate height of the top of the nearest mountain or hill. And so if you look at where these black arrows are, they correspond to where we see spikes in the average bias. So this indicates some of the impacts that the topography might have in these agreements. And moreover, if we look at what's happening in Whitehorse and Squamish, we see that the biases are negative in the valley, so the winds are estimated by the model, and then above the mountain canopy, the biases all switch to positive, so their winds are higher in the model compared to the observations. Now this is just done for 3 sites, so it's important to note that we need to sort of extend this to see, is this only happening at these 3 sites, or is this sort of happening elsewhere, and as well as in some of the other models. So another thing we looked at, using some of these enhanced observations we have at these sites, is a phenomenon that we're noticing at our Callaway data that we haven't really seen elsewhere, which are stratified wind and water vapor layers that were occurring in the troposphere, so from the surface up to about 7 kilometers in altitude. And so what's shown here, these are the results just for wind, but we found similar results for water vapor. And this was observed from our Doppler LiDARs, our Ka-band dual pole radar, as well as we got some snapshots from the radiosonde and our water vapor LiDAR observations that have detected stratified layers in various thickness, up to sometimes 4.5 kilometers thick. And when these layers occurred, they were very long lasting. So sometimes they lasted 27.5 hours before it would kind of dissolve and break up. They also occurred at high frequency, so 40% of the time we saw these layers occurring. So over 64 observed events during the YOPP period. So what I mean by stratified wind layers, if we look at this figure on the left here, this is a time-lapse video from the Ka-band radar, and what the Ka-band radar here is looking at is a vertical slice through the atmosphere, an RHI scan. So this is height as a function of the horizontal distance, going out to 15 kilometers on both sides. And this is a plot of the Doppler velocity. So reds would be Doppler velocities in one direction, and greens are Doppler velocities in the opposite direction. So if you pick a column and look upwards in altitude, you'll see that the Doppler velocities are alternating green, red, green, red, green, red, green, red as you go up. And what this corresponds to, and we saw this with the Doppler LiDAR, is your wind direction is shifting by over 90 degrees, in some cases 180 degrees, as you go up in altitude over a very, very narrow band. So lots of wind shear where you see these stratified layers. And we saw the same thing for water vapor, where we see these stratified layers from very high to very low concentrations of water vapor all the way up to sometimes 7 kilometers above the ground. Then we did some preliminary comparisons and analysis of what does the NWP model, forecast model look like, and we found that the forecast bias was amplified or reversed when these stratified layers were set up. So this warrants some sort of further investigation to look at why this is occurring, but also is this occurring at other sites? In the literature, these layers have been detected in the stratosphere, higher altitudes, but not so much in the troposphere. So this was something new that we wouldn't have seen if we haven't placed some of these new observations on the ground. And of course, the final note is there are implications to aviation nowcasting. So if you imagine a plane trying to land at a Callaway during these wind shears, it's a bit of a bumpy ride. And finally, I'll just end with one of the processes that we're looking at right now, which is the diurnal water vapor cycle in the Arctic, which is a critical component of the larger hydrological cycle. Now, there are very few measurements of the Canadian Arctic diurnal water vapor cycle, and there's pretty much no height resolved studies of the diurnal water vapor cycle worldwide. So when we're talking about the diurnal water vapor cycle, essentially what we're doing is we're just fitting a sinusoidal function with a 24-hour and a 12-hour component. But it's this 12-hour component, this S2 component, that is not well characterized or explained in the literature. So I'll talk about that more in a minute. And this is important because improving the diurnal cycles in models leads to forecasting and reanalysis improvements in larger scale processes. And so this has been being led by Shannon Hicks-Jalali, who's a postdoc in our group. And what we've done is we've used observations from a new pre-production Vaisala dial system. And we've done comparisons to ERA5 reanalysis, the GEM HRDPS, and then we also looked at the GPS at a Callaway, which provides integrated water vapor, so total column water vapor observations from the ground as well. And what we've obtained, this study which was published last year, was the first height-resolved diurnal water vapor cycles. This is for a Callaway. So the figure on the right shows the top panel is the results from the dial. So these are at in height, we fit the diurnal cycle as a function of 24 hours, so this is local solar time. The middle panel there, or towards the bottom, is the same fit, but for the surface station, so it's standard 2-meter height. And the bottom panel there is the results from the GPS, so the integrated water vapor amount, so the total column of water vapor. So the net cycle from the GPS is shown in black, and the red and blue correspond to the 24-hour and the 12-hour component. I apologize, it might be a little bit difficult to see there. But what we've found in the study is that the low-altitude Vaisala dial cycles show good agreement with the surface station cycles. So essentially what we're seeing is around local noon, you see reds, which mean increasing water vapor, and then as the sun goes down, you see blue, so decreasing water vapor, and you get that nice 24-hour cycle of water vapor. And this 24-hour period dominates within the boundary layer. However, the GPS exhibits a very strong 12-hour component. So that's this blue curve that you see in the very bottom panel there. And this could imply that the 12-hour cycles dominate at higher altitudes. And so sure enough, we see that the dial measures an increasing contribution from the 12-hour component above 1 kilometer, which corroborates the results from the GPS. And so what we've been working on now, we just submitted a paper, is comparing these cycles with ERA 5 and the ECCC NWP model comparisons, looking at both the dial and the GPS. And so for more information, please see the talk by Shannon. It's actually not tomorrow, it's today at the session at 1600. Perfect. So in summary, there's enhanced observational data sets available during the entire YOPP period, particularly during the 2 SOP periods that include additional radiosondes, buoys, in situ snow, ice monitoring, as well as 2 aircraft campaigns. There's high-resolution observations available at a Callaway and Whitehorse from these 2 supersites that are available on our data portal, but also as published MODFs that were talked about earlier in some of the earlier talks. There's enhanced ocean snow and ice monitoring in several other locations, and new products that are in development, looking at ice stress measurements off the Labrador coast, as well as the blizzard and fog probability forecasts. And now these forecasts are available both nationally and internationally on the public data mart server. And perhaps more importantly, the model verification evaluation process studies that are being conducted, and there's still more currently underway. So showing examples of what we've seen from winds, water vapor, but also looking at NWP model assimilation, intercomparisons, and process studies using these MODF files. So thanks very much, and welcome any questions.
So thank you so much for this nice overview about the use of the data of these 2 super sites, and also to keeping on time. So we have time for question and for discussion on this aspect. Yes, David?
Very, very nice talk, lots of interesting observations. So I'm wondering if you're working with the modelers to actually assimilate some of this, particularly the winds and maybe the moisture, which should be easier variables to assimilate, rather than just test out the models.
Yeah, that's a great question. So we've done preliminary assimilation impact studies. The nice thing about the way for instance, wind, the way the Doppler ladder works is if we can first characterize its bias, which we've done, and then we can try to assimilate it as if it were a radiosonde profile, the difference being, the temporal resolution being much higher. This is something we've looked at. The problem that I didn't really articulate with these LiDAR that we have, the LiDAR instruments, is their vertical range is very limited. So if you have a cloud base, it's not going to see above the cloud base. And more so, they only see pretty much throughout the boundary layer. So if you're only getting winds in the boundary layer, that means that your impact, when you assimilate these observations, it's very short term, within 6 hours or less. At least that's what our preliminary studies have indicated so far. So there's some limitations there, although there are certainly advantages, and certain groups have looked at some of the positive impacts, particularly if you place the LiDAR upwind, your positive impact is shown downwind, and you can get some positive impacts in terms of precip forecasts, for instance. So something that we're looking at, but there is that challenge where the instruments really just don't punch high enough to have sort of that global impact that we would like.
Yes?
A related question. Do you plan to continue to produce these useful merged data files in the future, perhaps pushing towards near real time to that end?
Yeah, great question. Definitely continue to plan to produce these, MODFs and, release the products. The nice thing about the MODF structure is once it's set up, it's easy to maintain and just run as you go. MODF in real time, that's a good point. I don't see why we can't do that. It's just a matter of writing the script. So yeah, I mean, that if it's beneficial, we certainly can do it.
Maybe to jump in on this question about the real time for MODF, there is no post-processing about the measurement of flux you need to do?
Yes. So There's, for instance, let's say quality control some of the data sets. What we have to do is we process everything sort of in real time at the sites, just because transferring data south from a Callaway is an absolute nightmare. So a lot of that is already sort of done on the fly using the computers we have at the sites. So that makes it easier than if we have to bring it in the MODFs. We already have everything that we kind of need to do so. So it should be possible.
Okay. So one more question? No? Okay, so I think we are on time for the coffee break. I would like to thank all the speakers for this session. And we will come back in 30 minutes.